Well, thank you. Yeah, I'm Tadeu. If you want to talk to me afterwards and you're worried you can't pronounce my name, don't worry about it. You can just say it however you like it, and I'll answer. I won't be mad at you. So yeah, I work on JavaScript Core at Apple, and I wanted to talk a little bit today about our new WebAssembly interpreter. So if you haven't heard about JavaScript Core, it's the VM that ships with WebKit, and WebKit is the browser engine that powers Safari, among other browsers. But Safari is the main client for us at Apple. And what I wanted to do today was just give a brief overview of how the VM works, how do we execute WebAssembly, and then dive a little bit deeper in the interpreter, and then finally share the results that we've seen now that we do have the interpreter. So let's get started. If you have seen anything about JavaScript Core, you might have noticed that we do like JIT compilers. We have quite a few of them. Among JavaScript compilers, WebAssembly, regular expressions, CSS. We also JIT some DOM operations. So what have you, if we can use a JIT compiler for it, we will. But yeah, also a couple interpreters and one more to come. But of course, today's everything about WebAssembly, so we'll be focusing on these two. Since the very beginning, we've had two compilers for WebAssembly. We call them BBQ, which of course stands for Build Bytecode Quickly, and OMG, which again, of course, stands for Optimized Machine Code Generator. BBQ is what is a less optimizing JIT, and OMG is a full optimizing JIT. OMG, right? What that means is actually that they both initially share the same backend, which we call B3. That's the backend that's used by our highest, the most optimizing JavaScript tier. And the only difference at first was that the BBQ would invoke B3 with -0, which means don't run any optional optimization passes. And OMG would just run it with -02, which means run every optimization you know about. And how did that work, right? Like, how did it perform? So in order to evaluate that, we need benchmarks. Today we're going to be looking at 3 benchmarks. So the first one wasn't originally a benchmark. It was a demo. It's called EpicZen Garden. It was used by Apple when Metal came out. And then I think it was Mozilla that compiled it to WebAssembly when they released their WebAssembly support. It is a nice benchmark because it's a 40 megabyte WebAssembly program. So if we want to see like how fast can we generate code, there's plenty there. We will also look at JetStream 2, which is a JavaScript and WebAssembly benchmark that was built by WebKit. For today, we'll be only focusing on the WebAssembly subtests, and we'll look at them. We will evaluate startup and runtime individually. Even though if you go to the website, it's going to combine and give you a final score, we'll keep that separate so we can see how each change we make to the engine affects both of these things individually. Last but not least, we'll look at the benchmark made by PSPDF kit. They compiled their PDF engine for the web using WebAssembly, and they also released this awesome benchmark. So we'll also take that into account. So again, just to bring it back, we're looking at the original. This is what we shipped it with at the very beginning. 2 tiers, both using B3, and this is how we did. So for now, all the bars are the same. This is just our baseline. Everything is 1x, even though there's a bunch of different numbers here. There's nothing to compare against, so it might seem like kind of random numbers. I just want to point 2 things out here. So the first one is that Zen Garden is in a separate block by its own that says compilation. And compilation and startup might seem similar. Compilation is not running any code at all. It's just how fast can we generate the machine code or bytecode or whatever, like have it ready for execution, but no execution whatsoever. Well, startup might run some setup code. It's going to get your WebAssembly code ready to run the functions. So it might run like things that would run in your C program before you call main or something like that. And then finally, runtime completely ignores compilation, startup, and it's just like how fast does your program run after it's ready. The second thing that I want to just bring out is that we can see, for instance, for Zen Garden, we take over 4 seconds to compile. If you have that in your web page and we're waiting for it to show up, that's not ideal, right? Ideally, you want to get things going faster. So we already knew about that, and last year, we changed BBQ to use a new backend called Air. New for WebAssembly. originally, what happens is that you emit some B3, which is an intermediate representation, that will run all the optimizations, and that will then be lowered to air. So air is lower level than B3. So now we're going straight into the lower level, which means that there's less optimizations to be run, like less work to be done, so we can get the code out ready to be executed faster. And this is an improvement we saw. So we can see that it really improved startup times. Like it's about 40% for compiling Zen Garden, and over 2x for over 50% for PSPDF kit. We also improved runtime on JetStream 2. Like we start executing faster and we make progress, while the slower compiler that's going to generate better code is doing its work. We did get a little bit worse in runtime for PSPDF kit, but compared to how much we improved the startup, we figured that was okay. Acceptable is probably the best word here. But still like almost 2.5 seconds to compile Zen Garden. Maybe we can still do better, and that's when we decided that we could add an interpreter. So the interpreter is called LLInt, which stands for low-level interpreter. It's the same name as the JavaScript interpreter. You can see that I'm not quite as creative as some of my colleagues. Unfortunately, I'll never forgive myself for that missed opportunity. But that ship has sailed now, it's official. Okay, so how does the interpreter actually work? So it turns out that it was easy to write the interpreter. And what I mean by that is a lot of the work was done for me, right? Like we already have this JavaScript interpreter, and it's very similar to what we have to do. We can reuse a bunch of the stuff that have been built over years by other people that work on JavaScript core, like my colleagues and people that no longer work with us. So this has been built for a long time, and all I had to do is just reuse it. So we already have this language, this portable assembly language called offline WASM that already supports all the backends that we run on. And we just recently released the new bytecode format, which I'll not dig into here, but we have a blog post about that if anyone's interested. So all that stuff was already there. All I needed to do was just add support for the instructions for WebAssembly. And it really helps that the instructions in WebAssembly are really simple. And I mean simple here in terms of complexity. So if you look at them, it's like add two numbers or subtract two numbers. There are more complex instructions, but the bulk of it, they're really simple. And this gets even easier because we already had the JIT that emitted this code. So all I really had to do is just look at the JIT, what instruction does it emit, because most of them map one-to-one to an instruction that the CPU has, and then just copy it to the WebAssembly, to the offline WASM. So, why is it worth a talk then, right? I wish it was that simple. So of course, you start doing things, and then you run into problems. So the first problem was, I should probably say challenge, not necessarily a problem, with our calling convention. So the calling convention determines how do you call a function, right? How do you pass your arguments? How do you set things up? And in JavaScript, if you have some function that wants to call some function called foo, that can either run in the interpreter, or you could also have some JIT code for that function. Now, let's say you want to call a second function, maybe called bar. Again, creativity, right? You might be running some JIT code, and then the JIT code is separate, right? The JIT code was generated only for that function, so they're completely individual. Or you might also be running bar in the interpreter, but the interpreter is a shared piece of code, so you need some way of tell the interpreter, like what function are you trying to run, right? Like, do you want me to run foo, or do you want me to run bar? And the way that works in JavaScriptCore is that we use the callee, is how we call it. So you just set that in the stack, and the interpreter knows how to read it, and that tells the interpreter, I want you to run this function. So that works, right? It's done. Well, in WebAssembly, it's a little bit different. So when you want to call foo, originally, the only option you had was JIT, right? We had two JITs. There was no interpreter. Since that code was generated specifically for foo, why do you need the callee, right? You know the function you're running. There's no interpreter. There's no dynamic bits about it. Well, it turns out that we actually need the callee. It's used for other things, like if you have exceptions, stack unwinding. I'm not going to talk too much about that. Just trust me, it needs to be there. But it can be put there by the actual JIT code. So we don't have the same need to know that ahead of time as JavaScript. But now I come along, I try to add the interpreter, and how do we tell the interpreter which function do we want to run? Well, at least for me, my first thought was like, well, I know how to do that. I've seen that before. You take that, and you do that in the caller, right? So now the interpreter just reads that, exactly the same as JavaScript. It's easy, it's done. Well, not quite. Technically, it's possible. It's done in JavaScript, but it turns out that when you're dealing with WebAssembly, the way we do function calls, you have to stop the thread in the middle, repack those addresses. Things get really nasty. We had some really bad bugs, and I spent maybe a month trying to get that working. I was like, well, you know, maybe it's time to put my creativity to work somewhere else other than naming tiers. So yeah, back to the drawing board. And the way we make it work is actually maybe interesting. It's not, well, okay. So what we do is that we meet a tiny bit of JIT code that we'll just write that callee, and then we will jump to the interpreter. So when we first release the interpreter, the first question is, can we run without the JIT now? And the answer is no. You still need JIT code. And unfortunately, that's not the only place. But that's just to illustrate, yes, like even though it's an interpreter, we still rely on some pieces of code that has to be generated at runtime in order to get it working. But it works now. It's good, I guess. Yeah. Second bit about the calling conventions was arguments. So again, back to JavaScript, just so we have a reference. If you want to call the same function, again, creativity really striking here. You want to pass one argument, let's say 42. The way it works, you put that on the stack, and then you go either to the JIT or the interpreter, to the lint. It doesn't matter. They both work the same way. And then that piece of code knows how to read the arguments back from the stack, so they're both accessing the stack. But with WebAssembly, of course, it couldn't be the same, right? That would be too easy. When you want to call foo, instead of just putting it on the stack, what you do is you put that in a register. And that makes sense, right? It's more efficient. You don't have to write to the stack. You just put that value in a register, and now the JIT code knows how to use it. It knows that the argument is going to be in that register, so it knows how to use it. But again, here comes the interpreter. How do we do that? Well, there's two problems here. The first one is that there's no way of talking about machine registers in the bytecode, because the bytecode is not machine dependent, so that's the first problem. And the second one is that the interpreter uses those registers, right? Those are the CPU registers. It has to use for things like, while it's getting our code set up to run, even before it has the bytecode, it uses that register to get things done. We can work around that, so what we can do is basically, before running any code, before reusing that register and losing that argument, we can just put it on the stack. Well, that works. But now we have a second call to, again, another function called bar, but now we have two arguments. And you know, the first part is the same. You just put the first argument in RDI, and I'm just using like x86 register names here, doesn't matter. You put it in one register, then you put the second value in the second register. But now you didn't save the second register, so you know, we've done that before. You're gonna reuse that register, and you're gonna lose that argument, so you put that in the stack, and it's all well. But since that piece of code is shared, we could be running a function that takes no arguments or a function that takes all arguments. How do we deal with that? And given our calling conventions, you can have the worst case scenario 16 registers. So 6 or 8 non-floating point arguments, so that would be integers, pointers, anything like that. 6 on x86 and 8 on ARM, and 8 floating point arguments. Well, the way we do that is every time you enter a function, you take all of those registers and you put them on the stack. You don't know if the function could be using all of them. And then comes multi-value. So once you're done with the function might be returning again 16 values. So we have to put all of those, take all those values from the stack and put them back into registers, so the function who called you knows how to read those results. It wouldn't be too bad if it stopped there. Every time we call a function, again, we can't refer to the machine registers, so you have to reserve space for those 16 arguments in the stack, and then copy them all back into registers, because we might be calling to JIT code, and those expect those values in registers. And again, multi-value, so that function might return 16 values, so you have to copy them all back. What does that actually mean in practice? Well, if you have a function that does nothing but just call another function, you're going to write to the stack 32 times and read from the stack 32 times. That brings me to the next topic, tearing up. The interpreter is not terribly fast, as you might have inferred from the last slide, so we want to get out of there as soon as possible. We want to move on to JIT code, right? That's faster, and we just want to get to that point where we're running our code faster. The way we do that is that we have counters to evaluate how many times are we running that function. Should we JIT it? Is it worth it? Because we spend time to compile that function. We will increment those counters every time you enter a function, every time we execute a loop, and every time you leave the function. So the last bit might be confusing. I had questions of why do you do it when you enter the function and then you leave the function? Well, since we have a concurrent compiler, sometimes we'll hit that count exactly when you leave the function. That will allow you to start compiling that function, and maybe by the time you call it again, we're ready with the compiled version and we can start executing the faster version of the function. So how does that work in practice? So if we have this small program, suppose you just have a function f that will do some really expensive computation, and then it's going to return you a Boolean that tells whether you should keep computing or not. And then you just have the main loop driving that and calling f again and again. So if we look at the timeline of this function, of this program, we'll start by running main, supposing like someone calls that, that's your main function, and it's going to start out in the interpreter. And then eventually it's going to call that function f, which is also running the interpreter because we have never run it yet. If you keep calling it, eventually we're going to hit that counter, and then we'll trigger a compilation, which will start in BBQ, which is the first tier. We'll keep running in the interpreter while we're doing that compilation. We don't want to stop making progress. Once that's done, that's going to notify f and say, like, well, I have a faster optimized version of this function, so you can run that instead. Next time we call f, we'll go into the BBQ compiled code. But if we keep running it, we're going to hit that again. Then we start an OMG compilation. Keep running BBQ until that's done. That's going to notify the same process. And then at some point, we'll just be running OMG. So the problem with that picture is not f, right? It's main. If you had something very expensive going on in main as well, now we're stuck in the lint. And again, it's not super fast. We want to get out of there. The way we get around it is that loop counter is going to trigger at some point, and this is just an implementation detail, but if you trigger in the loop, you go straight into OMG, you skip BBQ. That's just a detail. So you trigger that, and it's the same way as with a regular function call. You just keep running the interpreter until that's done. Once that's done, notifies you, and we do what we call an on-stack replacement. So you save all your state. You're in the middle of the loop. You copy all that state, and you move on to native code. And you just resume your loop exactly from where you were before, but now you're running faster code. After that, we had a working interpreter. We had tearing up. But there was still one thing that we could do better, which I called here constant and local propagation. So when we looked at the generated code, a lot of the bytecode was just moving values around, right? So we do get local that will get you a temporary register, virtual register, and copy that value there. I'm going to illustrate it in a second. Every time you get a constant, you have to move it into a temporary location. All that moving turns out that generated a lot of instructions, and it took a lot of time to execute as well because of dispatching in the interpreter. So the way we got around that is if you look at this program, you just suppose that's inside a function. You take an argument, you add 1, and you return it. If you want to generate bytecode for that, we start from the inside of the function. So the first thing you're going to do is the local, the get local. And the way that works is that we save that the lock is a virtual register, as we call it. It's just a space in the stack that we allocated for each local variable we have in that function. So we reserve that lock 0 for that local that you know because of the WebAssembly declaration that's going to be there. So once you want to get that local, we just create a new temporary location for that value and copy it there. When you have a constant, we do the same thing. You allocate a temporary place for that constant, and you move the constant there. When you have an add, you add a temporary place to put the result of the addition, and you just add those two numbers, and then finally you return that. Well, if we look at it, we're adding lock1 to lock2, but we know who those are, right? We just moved them there. We moved the lock0 into lock1, so we know that lock1 and lock0 have the same value. We also just moved the 1 into lock2, so we know that value is there. So what that let us do is just replace those registers with the actual values. And then we can completely eliminate that code by basically cutting the size of the function in half. We have to be careful with that, though, because if we replace that constant with something that writes the same stack location, so let's say here like local.t, now we're still using lock1 there, but after we move lock0 into lock1, we're overwriting that value, so those two things no longer have the same value. So if we replace lock1 with lock0 there, now we will just have the constant 1 instead of whatever argument your function received in the first place. So that's no longer safe. But that allowed us to reduce the size of the bytecode by a lot. So how does that interpreter actually work? So back to the graphic, that's what we had before. So that's in blue, our original configuration. In green, what we have shipping right now with our Air backend. So first, we'll look at the compilation. The reason it's easier to talk about compilation is that since there's no execution, we're only comparing B3 to Air to the interpreter. There's no tiering up, there's no other tiers involved, so it's easier to compare. Later on, we'll have to make other decisions. But for now, if we just compare how fast they generate code, it's perhaps unsurprising that the bytecode is a lot faster, right? We're doing a lot less work. The bytecode translates almost one-to-one with WebAssembly. There's no machine code, there's no intermediate representation, no lowering, no optimizations. It's a lot faster, so about 8 times faster. But now, when it comes to runtime, that's where we were at, and now we have to decide, well, how do we put the interpreter in this picture, right? Do we replace? Do we move things around? Which tiers do we use? Well, the original, the first attempt was just, well, let's get rid of barbecue. Let's put the interpreter there. That keeps things simpler, fewer tiers, less code to maintain. And again, perhaps not very surprisingly, for startup, it worked great, right? Like, startup is mostly dominated by compilation, so it was just a lot faster. But when it comes to runtime, well, things weren't quite as good. And it kind of makes sense, right? We're running the interpreter until we finish compiling, but we're compiling that code with the slowest, most optimizing compiler we have. So we end up just stuck in the interpreter for a long time, and we make very little progress until that code is done. So that wasn't the best solution. So what we did instead, next, is we just tried, well, let's keep the compilers we have, and let's just add the interpreter there. Let's go with the 3 tiers and see what happens. That looked better. So startup still even progress on JetString 2. PSPDF Kit, not quite as good, but just a little bit. We even got some runtime improvements on both of them. So for PSPDF Kit, okay, it's neutral. I wouldn't call that a progression. But for JetString 2, it's a significant progression. And that's because we can start executing code faster. And by the time the next year is done, we already made some progress on the execution of that program. There's still one alternative solution. Instead of maintaining 2 backends, so Air and B3, we could just go back to a world where both of those tiers share the same backend, and they both run with B3. We also tried that, and that gave us mixed results. So we can see that the startup was a little bit worse in PSPDF Kit, about the same on JetString 2. But runtime on JetString 2 just got a lot worse because, again, that compiler is using the same backend, B3. Even though it's not doing quite as many optimizations, it's still a slower compiler. It does more work. It generates better code. And we end up spending more time in the interpreter. Somehow, we got the fastest result on PSPDF Kit runtime. I honestly don't know why just yet. I gathered those numbers. I was like, that's interesting. But still, even with that, if we look at startup, we also got the worst result for startup on PSPDF Kit. So if we look at the results overall, what gave us the best results was the interpreter plus the Air backend plus OMG. That gave us the best benchmark results and the best balance between startup and runtime. So that's what we ended up with. That's what our WebAssembly tiers look like now. And in the context of the whole engine, These are our current state of things, and that's all I had for today. Thank you.